Good. Then I will open my screen. Okay. So my screen is visible to you, right?
Yes, sir.
Okay. Okay. So this week I have only one query, and I have sent a personal email to that person, and I can see that this person is here, joined today. So, is it a necessity to elaborate it further?
Sir, no, sir. Yes, I could create a construction from that later. Yeah, I got it.
After whatever I have mailed, after that it's fairly straightforward. Okay.
Hello.
Okay, fine. Fine. So, let us go to the tutorials directly then. Okay, so today we will solve a few, I would say, simpler kind of exercises. More complicated exercises will be covered later. So I start with this. So first let me go to this section. Good. Okay. So I start with first some very simple fact about reductions. So let us say that Q and Q prime are two problems such that there is a polytime reduction from Q to Q prime and another polytime reduction from Q prime to Q. So if we can have some such things, we say that Q and Q prime are polynomial time equivalent. So in other words, because of these two reductions, it follows that Q is solvable in polynomial time if and only if Q prime is solvable in polynomial time. Or stated differently, if Q cannot be solved in polynomial time, or I would say Q cannot be solved in polynomial time if and only if Q prime cannot be solved in polynomial time. So that is basically the, I would say, an important idea behind dealing with polynomial time equivalent problems. So now, what you are asked to prove, it's fairly straightforward, is that any two NP-complete problems are polynomial time equivalent. So if you can find a polynomial time algorithm for any of the NP-complete problems, all other NP-complete problems can be solved in polynomial time. Okay. So how to prove this? Yeah, I think this is just a couple of minutes thinking, should not be more than that. Yeah, actually, I asked you to prove. There is nothing to disprove. A fairly straightforward question. Yeah. So any suggestions?
So we can use the fact that both are NP hard, and so uh, like both Q and Q prime are NP hard, and Q will reduce to all other NP hard problems, not to all other problems, and so and the reverse thing will be true.
Okay, it's not that I understood what you told very clearly. Anyway, so let's not waste too much time on this simple thing. So first of all, never forget the two requirements of being NP complete. Both are very important. One, the problem that we are talking about must be in NP. It should be an NP problem. And second, it should be NP hard. Okay, both the things are needed. So if I now look at the problems Q and Q prime, it is given that both are NP complete. So I know Q is in NP, Q prime is in NP by requirement 1. And by requirement 2, so 1 implies this, 2 implies, so Q prime is NP complete. What does it imply? Or NP hard, I would say better. This implies that, by definition, every problem in NP reduces in polynomial time to Q prime because it is NP hard. So in particular, Q is a problem in NP. So Q also reduces in polynomial time to Q prime. This is by definition of NP hardness. So Q less than equal to Q prime by definition of NP hardness, and likewise since Q is NP hard and Q prime is in NP, Q prime also reduces to Q in polynomial time. Okay, so this is essentially an immediate consequence of the definition. Okay, so there should not be more complications in it. Okay, so I switch to the next one. This is fine, right?
Yes, sir.
Okay, good. Okay, maybe I will do this. Okay. Yeah, so this is where you are asked to prove some kind of reduction. And in this case, of course, reduction is not so difficult. Okay, so I define the problem double set as the problem of deciding whether a given Boolean formula has at least two satisfying assignments. So it is not only satisfiable, it is satisfiable by at least two assignments of the variables. Okay. So you prove that this problem is NP complete.
So we can use a reduction from SAT, and we can just append extra variable and a new variable with a clause of the form x1, or like if the variable say xn is not used, then xn or xn bar. Then for if and only if the original, like the problem which was given in SAT, if that is satisfiable, then if xn is 1, then also we have a solution, and if xn is 0, then also we have a solution. Otherwise, there is no solution because the original problem which was given does not have any solution.
Okay, so I will elaborate this, but let me see some. Take any two problems, pi 1 and pi 2, which are NP complete from definition. Okay, fine. So this was the earlier question. Fine. Okay, so now there is a suggestion. Before elaborating it, let me do one thing. So whenever you prove something is NP complete, it's not only the reduction that you will do. First, you have to show that, never forget this step. Double SAT is in NP. This step you never miss. Usually it is trivial to prove something is in NP. Usually, of course, within quotes, not necessarily always. So how do I proceed?
So as long as like the certificate for double SAT should be just 2 truth assignments.
Okay. So when you prove something is in NP, there are two ways. First, or I would say first or more common approach is to provide a succinct certificate. Okay. And second possibility is you propose a non-deterministic polynomial time algorithm. We have seen that these two notions are essentially equivalent, so it doesn't matter which one you do. But usually certificates are a little bit easier for us to I would say, present. Okay. So certificate, two different truth assignments. Of the variables for which the formula evaluates to true or one or whatever you say. And you can just plug in the values of these truth values of the variables in the formula and figure out whether this is actually a true certificate. So first of all, we check that these two assignments are different. Simply plug in the values, truth values in the formula to evaluate the input formula, maybe 5, and you show that in both the cases 5 evaluates to true. Okay, so this can be done in polynomial time in the number of variables plus the length of the formula. That's important. Then you show is NP hard. Again, there are two ways. You propose a generic reduction from any NP problem to your problem. But this is in general a very difficult proof. Actually, we have not covered any such proof explicitly. Like SAT is NP complete, we have simply taken the result from Cook-Levin's paper. CNF SAT is NP complete, that is also something taken from Cook-Levin paper, or papers, I would say. There are actually two papers. And yeah. The second option is you make a reduction from one already known NP-complete problem to the new problem. Okay. So what is suggested is that we make a reduction from SAT to double SAT. And the reduction suggested was this: if we have a formula Phi1 to Phi(xn), an instance for SAT, then we generate the formula Phi, let's say, hat x1, x2, xn, and I just introduce a new variable y. Take the old formula, and it was and you suggested, right? Yeah.
Yes, sir.
And y or y complement. Straightforward reduction. Now, if this is satisfiable, then there is at least one truth assignment of x1 through xn for which this quantity, which is same as this quantity, evaluates as true. Take that truth assignment of x1 through xn and take any of the truth assignments of y, irrespective of whether it is true or false. This evaluates to 1, and 1 is 1. So if this is satisfiable, this is double satisfiable. Conversely, if this is not satisfiable, then whatever truth value you assign to x1 through xn, this quantity evaluates to false or 0. So whatever truth value you give to y, this will evaluate to 1, but 1 and 0 is 0. So phi is satisfiable if and only if phi hat is double satisfiable. Happy? This is one thing. And the second observation is that this reduction should be doable in polynomial time. Okay. Polynomial time means polynomial in the size of the formula plus the number of variables. That is clear, right? If there are n variables, by looking at the formula, you can actually figure out how many variables are appearing there. Then just add a new variable. I have given the name y, you can give the name xn plus 1 as well. No problem. Okay. And then just copy this formula followed by this thing. This is doable in polynomial time. Okay. So there are several things. This is an easy example, but it gives you a drill of several things. First, never forget this step, the first step. Second, you propose a reduction given an instance of this input problem. You produce an instance of the output problem. Explicitly you mention what this output instance looks like in terms of the input instance. Okay. You also have to show that if this belongs to the accept instances, this should also belong to the accept instances of this. And if this belongs to the accept instances, this also belongs to the accept instances of the source problem. And final thing you have to establish, that is the reduction or the conversion of the input instance of this to the input instance of this should be doable in polynomial time. All of these things do hold here, and therefore this is a valid reduction. Happy or not?
Yes, sir.
Right. Okay. Okay. So, anyways, this is a simple example. Next one is also almost equally as simple. So, a little bit more complicated, but now here I have not assumed this set or double set instances to be in the conjunctive normal form. They may be anything. Okay, not necessarily in the conjunctive normal form, but now I assume that a formula is given in the conjunctive normal form. So it's called a CNF formula. Okay. It is called not all equal satisfiable if for some truth assignment of the variables, each clause has at least one true literal and at least one false literal. So this essentially implies that each clause is true because it is an OR of literals. So each has one true literal and one false literal. So this will matter actually. So this is basically a satisfying assignment. It says that the formula has a satisfying assignment for which each clause is not all truths. Each clause has to be true, but there is at least one false literal. Okay. And by not all equal set, I decide the problem. I denote the problem of deciding whether a Boolean formula in the conjunctive normal form is not all equal satisfiable. So prove that this problem is NP complete. Okay, maybe think about a bit and let everybody think. Maybe after 5 minutes or so, I will ask for suggestions. Okay, good. So any suggestion? Okay, first of all, never forget this. This is in NP because again a certificate is fairly easy. That is a satisfying truth assignment for which this extra condition is satisfied. So the certificates are easy. A satisfying assignment with the stated property. Okay. Then you have to show that this is NP hard. So what is the natural, I would say, problem from which I will reduce?
CNF set.
CNF set, right? Because if I start with SAT and I produce an instance of NA SAT, and from a general formula I have to build a CNF formula. That is not necessarily a very easy task. But in view of the fact that we have also seen that CNF SAT is NP complete or NP hard for that matter, I can make a reduction from CNF SAT. Okay. So I will propose a polytime reduction from CNF SAT to not all equal SAT. This is also CNF SAT, but okay. Anyway, I will take a formula phi, create another formula phi hat, such that phi is in the CNF in the conjunctive normal form. Phi hat is also in the conjunctive normal form, and this phi is satisfiable if and only if phi hat is not all equal satisfied. So both phi and phi hat should be CNF formulas.
Sir, what has NAE SAT got to do anything with satisfiability?
Well,
Because
I do not understand what you really mean by that.
I mean, in the sense that for some truth assignment of the variables, each clause has at least one true literal and one false literal. So that doesn't mean that the whole formula has to be true or false.
No, first of all, it is true that it has to be satisfiable. Because if each clause has one true literal, then the formula is satisfied. But I interpret your question this way. What is the natural use of this kind of formulas? Is that what you essentially implied?
Yes, sir.
CNF SAT, okay, it's fine. It's a natural problem. But what is natural about this? Okay, my answer is there is nothing so natural about it. Some applications may require formulas to be like that. I do not know. So let us call it a concocted problem. The idea is that this is just an example to illustrate reduction. Okay. In fact, more serious reductions I will not cover today. Okay. Things like Hamiltonian path, Hamiltonian cycle, some of which are already covered, but something like subset sum, knapsack, partition, or balanced partition problem. These things we will look at later, which have more natural flavor. This is just an example to illustrate how reduction works. So if you are not very convinced that this is possibly a bad artificial problem, let it be, doesn't matter.
So here for each clause, we can add a new variable to the clause. Say the clause was x1 or x2 till or xn, then we will add a new variable and we'll make the clause x1 or till x or xn till and or y. Now, if that phi has a satisfying assignment, then I'll just set that y equal to false. So that will give me that. So in
Good.
that case, I'll get that phi hat is also satisfiable.
And conversely,
Yes,
this should be a
conversely, for the converse, I need to prove that if phi hat is satisfiable, then phi is satisfiable.
good. Your suggestion is good. In fact, I am going to do the same thing. Okay. So the suggestion is something like this. Can I write here or go to another page? Anyway, let's see. So let us take a clause in phi to be something like this. Okay, so the variables, let us say x1 through xn. And the clause may be something like literal 1 or literal 2 or literal, let's say this clause contains k literals. You can also reduce from 3 CNF sat, in which case k is 3. Anyway, it doesn't matter. But this each li is either a variable or its complement. Okay. So what I do, I introduce a new variable y. Maybe I have to separate. Okay. Change this clause to literal 1 or literal 2 or blah, 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 literal k or something like y. Of course, I could have introduced a fresh variable for each clause, but it's not necessary. I can take a single variable y in all the clauses. So where y is not in the set of variables involved in phi. Okay. So now I have to prove two things. Phi is satisfiable implies phi hat is not all equal satisfiable, and the converse. Now this is easy actually. If I take a satisfying truth assignment, let's say T1, T2, Tn. So this is a satisfying truth assignment for phi. What does it mean? This is a satisfying truth assignment. Therefore, each clause must evaluate to true. In particular, L1 or L2 or up to Lk, this must evaluate to true. That means there is at least one literal which is true. So if I take y equal to false, okay, then this converted clause has at least one true literal and at least one false literal. Okay. Then take y equal to false. Okay. And this is at least one true literal, at least one false literal. And therefore, if phi is satisfiable, every clause of phi hat is also satisfiable, but it has at least one false variable and at least one true variable. So in other words, phi hat is not all equal satisfiable. Okay. What about the converse? Or you can prove the contrapositive. Okay, if phi is not satisfiable, then phi hat is not almost equal satisfiable. But anyway, let's do this directly. The converse.
So for this, we can say that if we have a satisfying assignment for NAE SAT, say x1 till xn and y, then if y is false, then x1 till xn will be a satisfying assignment for CNF SAT.
Good.
And in case y is true, so in that case we can just invert all of x1 till xn, so we will get a assignment for CNF SAT.
Good. Okay, so that's it. So let T1, T2, Tn, and some value of y, let us call it theta, be a NAE satisfying assignment for phi hat. Okay, now I consider two cases. Theta is false. Okay. This implies that there will be at least, so this is false, and this is a not all equal satisfying assignment. So this means some of these remaining literals must be true. Right. So this implies that T1, T2, the same truth assignments if I take, satisfies phi. But it is also possible that this is true. Theta is true. The truth value of y, this is true. But this is a not all equal satisfying assignment. This means all these things are not true simultaneously. At least one of the literals must be false. Happy? Therefore, if I simply flip this truth assignment, so if I take T1 prime, T2 prime, Tn prime, this truth assignment satisfies phi. Happy? Okay, so prime is not visible here. T1 prime, T2 prime. Just flip the assignments. Okay. Y will anyway remain true. Okay, doesn't matter. But this has at least one false assignment. So if I complement every variable assignment, all these literals will be complemented. If there is at least one false guy here, it will become true. Happy?
Yes, sir.
Okay. So this is slightly more complicated than the previous one. Okay. So, but again, if you find this a bit artificial problem, don't worry. This is just an example. Okay. So we will not talk about much more about reductions today. Instead, I will consider something about a complexity class called CoNP, complement of NP. Okay. This is not already covered in the lecture. So that may be a problem. Okay. So it has some accept instances, it has some reject instances. And this is a decision problem. So I can think of a problem Q where this accept set and reject set are simply flipped. Okay. So if P rejects, Q accepts. If P accepts, Q rejects. Okay. So for example, if P is the primality testing problem, Q is essentially the compositeness testing problem. Okay. Something like that. Okay. And because this reject P and accept P, these are well defined. So the complement problem Q is also well defined given P. Okay. And now I define the complexity class ONP as the set of all problems P such that, or maybe I should have written Q here. Complement problem Q, of course, this is fine, no problem. So maybe just for clarification, a little bit more consistent with the notations. Let me write Q. Okay. The complement of Q is in N. Okay. So this is more of an introduction to this concept. So here are some examples. Obviously, SAT is a problem in NP. Therefore, its complement is definitely in CoNP. Why is primality testing problem in CoNP? Because
Compositeness is in NP, so its complement primality will be co-NP.
so compositeness is in NP because in order to prove some number to be composite, all that suffices is just produce a non-trivial divisor of that number, of that integer. Okay. So primality is the opposite, almost the complement of compositeness, because 0 and 1 are neither prime nor composite. So apart from this small thing, this thing. And before introducing the fourth and the third and the fourth problems, let me identify one important, I would say, issue about CoNP problems. So P is a problem in NP, and this complement is key. So this accept P has certificates. Okay. For example, a compositeness certificate is a non-trivial divisor of the number. Now, rejection does not have certificates for a problem in NP. But if I look at the complement queue, so these certificates are no longer certificates, but some kind of, I would say, some kind of proofs that the instance belongs to reject of queue. So this is opposite of certificates. Okay. So they are called disqualifications as opposed to certificates. Now, Q is the complement problem. Reject P does not necessarily have some kind of easy arguments, and therefore accept Q, the instances in accept Q do not have, need not have, I mean, easy ways of establishing that the thing that these instances are in accept Q. But if some problem is in NP, it has certificates, and these certificates behave like succinct disqualifications. So all problems in co-NP are characterized by the existence of polycized disqualifications. Okay. So tautology is, once again, the problem is this. Given a Boolean formula phi, it evaluates to true for all truth assignments of the variables. Okay, it's something like x or x complement. Whatever truth value assigned to the variables, it evaluates to 1 always for all possible truth assignments of the input variables of the variables. And if a formula is like that, it is called a tautology. Now this tautology problem is deciding whether a given formula is a tautology. Likewise, if for all possible truth assignments phi evaluates to false, other than that everything remains the same, then phi is called a contradiction. For no truth value, this is satisfiable. Okay, for everything it evaluates to false. And the problem contradiction is, given a Boolean formula phi, determine whether it is a contradiction. So why are tautology and contradiction ONP problems? So these are co-NP problems. So don't try to supply succinct certificates. You supply succinct disqualifications. So what is the succinct disqualification for a formula in tautology? Certain assignment variables, 5 values to false, then that assignment is a disqualification for tautology. Right. So a disqualification is a truth assignment for which evaluates to false. Likewise, for contradiction, give a truth assignment for which the formula evaluates to true. That's a disqualification for contradiction. Okay. So a truth assignment for which evaluates to true. Okay. So it's difficult, if not impossible, to find, I would say, a succinct certificate for tautology or contradiction. So under certain assumptions, this is never, we cannot have succinct certificates. Okay. But succinct disqualifications we have. Agree? The difference between NP and co-NP? Yes or no? Tell something. So the idea of
Yes, sir.
co-NP, yeah, and disqualification, this is important. Okay, so maybe I will just, I see, okay. Okay, so maybe you think a little bit about it. This is not difficult. So the question is, how does this complexity class look like? In fact, as the next example we will see, as the next exercise we will see that the class P is inside both NP and co-NP. So are these two classes equal, NP and co-NP? It's a difficult question, we do not know. But if this statement is, if this is true, if any NP complete problem is in co-NP, then these two classes, NP and co-NP, are equal. So prove this. Okay, so this is not exactly an immediate proof. So think a little bit, 5 minutes, 6 minutes, something like that. Then I will come back. There is a problem. I just have got a power cut. I don't know how to proceed. Definitely my UPS will not run long. I hope it will come back soon before the UPS goes down. Okay, so before any bad thing happens, so let me show you the exercises. Prove that the class P is in the intersection of NP and co-NP. I will supply solutions to all of this. So if my machine goes down, and like NP complete problems, you can define co-NP complete problems. So because these are just complements, and this is the final plan, proving that tautology is co-NP complete. Okay, so these are my, I would say, plan. So if I cannot complete this, of course, I have not set up my mobile data to work with this for the moment. So it may be difficult if the power does not come back. Okay, so maybe I just give you some small hints. So a problem Q is in co-NP, or it's co-NP complete if Q is in co-NP and Q is NP co-NP hard, which means every P in co-NP reduces to Q in polynomial time. So in some sense, if I look at the complement of this Q, the complement is in NP and the complement is NP hard. Okay. So in order to prove certain thing is co-NP complete, you may have to make a reduction from the complement of an NP complete problem. For example, here I can do a reduction from the complement of SAT to tautology. Okay, so it's fairly straightforward. Phi simply maps to the complement, but this is not language-wise complement, it is the Boolean complement. If something is not satisfiable, then its complement is always true. And like that. Okay. Here also I will give you a short hint. P is in NP. Why? Because I can take null certificate, which is definitely a succinct certificate. Because if the problem is already in P, we know how to solve it in polynomial time. We actually do not require any certificate to solve it and determine. Likewise, Okay, P is contained in co-NP because if a problem has polytime solvability, I actually do not require any disqualification. So it can be null. I simply solve that problem and determine whether that thing is a disqualification, that null certificate. So it is inside this, and therefore it is inside the intersection of NP and co-NP. So what is the classes? So it's something like this. This is NP, this is co-NP, and in the intersection I have the class P. Now what about the complement? What about the containment? Is P properly contained in NP? Is P properly contained in co-NP? Is P properly contained in NP intersection co-NP? So these questions are not yet answered because whether P is inside NP properly, so that is the P equal to NP problem. And that is an open problem. The most popular belief is that these two classes, NP and co-NP, are not the same. This containment of P inside the intersection of NP and co-NP is also proper. So, but these are all popular beliefs. We do not have any proof for these things. Okay, so yeah, so I think this is not so, I would say, immediate. It requires some lines of argument, and power is yet not back. So at any point of time, I will go out. Okay, so I will supply you a solution of this. So shall we stop here? Yeah, tell something.
So you'll send the like solution, right? Because
Yeah, I will do it. Immediately after power comes back, I will just formally send these solutions. I don't know. It's getting difficult to proceed. Actually, this thing is simply follow from the definitions anyway. So yeah, so I didn't want it to end at this abruptly, but yeah, it's difficult. Okay.